Welcome to the explainer. Have you ever stopped to think about how your email just knows what's spam? That email from a supposed prince with a fortune to share? Straight to the junk folder. Well, a lot of the time, the magic behind that is a surprisingly powerful yet simple algorithm. And today, we're going to break it down. So, how does it do it? It all comes down to a really clever tool that just plays the odds. And we're about to dive deep and see exactly how it places its bets. All right, let's get into it. First, let's meet our star for today, the Naïve Bayes classifier. And yeah, that word naive, it's actually its secret weapon. So what is it? Think of it like a detective. It's looking at all the evidence from past cases. That's our data to figure out the probability of a certain outcome. If 9 out of 10 times a suspect had muddy boots at the crime scene, the detective is going to remember that.
Okay, so here's the part that gives it its name, the naive assumption. And honestly, this is where it gets really cool. The algorithm it naively assumes that all the clues it's looking at are totally unrelated. For a spam filter, that means it thinks the word free and the word winner have nothing to do with each other. Now, you and I know that's not true, right? They're practically best friends in spam emails. But, and this is the genius part, making that simple, wrong assumption makes the math a whole lot easier. And the crazy thing is, it works incredibly well.
So theory is one thing, but let's see this thing in action. We're going to walk through a real-world example, step by step, so you can really get the logic behind how it makes its predictions. Okay, here's our case file. We've got data on 10 different companies. Our mission is to predict if a case is fraudulent or truthful. And we've got two main clues to work with. Were charges filed against them, and was it a small or a large company? Let's see what our model can figure out from just these 10 examples. So let's start with a specific scenario. Imagine we have a small company, and yes, charges were filed. To figure out the odds of this being fraudulent, we first look at the overall chance of any case in our data being fraudulent, which is 40%. Then we multiply that by the probability that these specific features, charges filed and small company, show up in other fraudulent cases. We do the exact same math for the truthful outcome, and then we just see which one is more likely. All right, on to the next one. This time, it's a large company where charges were filed. You're probably starting to see the pattern here, right? The formula is exactly the same. We're just plugging in the numbers for this new situation. It's this repetitive process that lets the model build a complete picture of our data. And we just keep going. We run this calculation for every single possible combination, including, of course, the cases where no charges were filed at all. This makes sure our model is ready for whatever new data we throw at it. So once we've crunched the numbers for every possible combo, we do a little housekeeping called normalizing. It's basically just adjusting the scores so they all add up to a neat 100%, giving us a really clear probability for each outcome. And voila, here's our final table. Looks pretty good, right? Our model seems ready for action. But hold on, there's a huge hidden flaw in what we've just done, a real ticking time bomb.
And this is where it gets really, really interesting. What happens when our shiny new model comes across something it has never, ever seen before in its training data?
This very question points to a massive weakness in our raw calculation. I mean, what if we'd never seen a fraudulent case from a small company in our original 10 data points?
See, here's the killer problem. Since we're multiplying a bunch of probabilities together, if any single one of them is 0, the whole thing becomes 0. End of story. Think about it. If a spam filter has never seen the word inheritance in a fraudulent email, it gives it a 0 probability. So the next time it sees an email with that word, the model will just decide it's impossible for it to be fraudulent. The whole prediction just completely falls apart.
But don't worry. Thankfully, there's a really elegant fix for this. It's a technique called Laplace smoothing. The solution is just so simple, it's brilliant. All we do is add a tiny little number, usually just the number 1, to every single count we have. That's it. It's kind of like we're pretending we've seen every possible outcome at least one time. And by doing that, we guarantee that no probability can ever be 0. And here's what that looks like in practice. For every count, we just add 1 to the top number, the numerator. Then, to make sure all the math stays balanced, we add the number of possible categories to the bottom number, the denominator. It's a tiny little tweak, but you'll see it has a massive effect on how reliable our model is. So now we go back and do it all again. We rerun
every single one of our original calculations, but this time we use our new, smoothed numbers. The core logic is exactly the same, but now our numbers are protected from that fatal zero frequency problem.
We finish up the math for the last couple of combinations, and now we're finally ready to see the improved, much more robust result. So, you might be wondering, was all that extra math worth it? Well, let's put the results side by side. I think you'll see the difference pretty clearly. Okay, have a look. On the left is our original model. On the right, the one with Laplace smoothing. See what's happening? The probabilities on the right are just less extreme. They're pulled back from the edges a bit. This means our smooth model isn't going to be so overconfident based on just the little bit of data it's seen. It makes it way more reliable when it bumps into something new out in the wild.
So here's the big idea. Without smoothing, our model is a slave to what it's already seen. A rare event can totally break it. But with smoothing, we build in a little bit of humility. We create a more conservative, more realistic model that doesn't overreact to its training data. It's just much better prepared for the real world.
And that really is the key takeaway. This isn't just about stopping an error from a zero. It's about making our predictions more balanced, more reasonable, and at the end of the day, a whole lot more trustworthy. And all of this leaves us with a really fundamental question, not just for this algorithm, but for all of data science. How do you strike that perfect balance between trusting the data you have and preparing for all the unknown data you haven't seen yet?